All right, welcome. This is the second talk of the afternoon session, UGM2020 for iRODS, and this is Ilari, live from home, the Royal Institute of Technology, KTH, and Ilari is going to talk about his work with moving things around using different Gpfs file systems. Go for it, Ilari.
Okay. So I just wanted to show my face quickly for a proof of life. So also as a disclaimer, I'm a bit sick and I'm currently in sick leave. So we'll see how this goes. But if you don't mind, I'll go hiding. I'll disable my video for the rest of the show. So figure out how to do that. Okay. Can you hear me good? Or do I need to raise volume?
Yes, you're still good.
Good. So I'll just get comfortable around here. So yeah, this talk is about data migrations, and especially the work that we did with Jason and Terrell late last fall with the new or relatively new parallel rule execution engine in iRODS. And yeah, so to give you just a quick background on the subject, so I'm basically working at the HPC Center of KTH, and KTH is a technical university in Stockholm, Sweden. And we are a member of a consortium called SNCC, which is also a member of a consortium called the iRODS consortium. And SNCC basically facilitates the HPC funding that goes around in Sweden. And of course, in addition to just HPC computing, we also are doing lots of data storage activities, both high performance parallel file systems and also scalable distributed storage systems. And of course, this means that we have to do lots of data management. And at PDC, we are hosting a part of a national storage platform, which is funded by SNCC, called SWISTOR. And SWISTOR is a bit of a heterogeneous project, which is currently running on 2 separate storage islands. The other one is the older one in Sweden, which is based on Dcache. And the newer one is based on iRODS. And these both are distributed nationwide systems, but they are being coordinated by the same framework. And of course, iRODS enables us to use various different kinds of heterogeneous underlying storage systems. And currently we are using both ZFS and Gpfs. And in practice, we are running our performance tier or a landing zone on top of Gpfs. And then our secondary tier is being managed by separate ZFS file systems, a set of ZFS file systems and hosts storage arrays. And this talk is about our need to shuffle around some data in our Gpfs cluster at KTH, because we need to upgrade the thing. And that includes reformatting physical file systems. And the reason for this is we bought our storage system late 2017. That is a IBM ESS Elastic Storage Server, which is based on IBM Power 8 servers and Gpfs. At the time we procured it, Gpfs was still running at version 4.2.3, which was the previous major version. And basically only after 2 months we had procured the system, IBM released Gpfs 5. And we were already aware of this at the time, and we basically decided to make room for an upgrade to GPFS 5 because we knew that it has features that we desperately need. The most important of those is the enhancement in space efficiency with respect to disk block allocations and splitting physical disk blocks into logical subblocks and allocating files on those. So the older version of GPFS was able to split the physical disk block into 32 fixed subblocks, fixed size subblocks, to each of which one can allocate the file. Well, in our case, because we need streaming performance, we had to format the file system in 8 megabyte blocks to get most of the on-disk capacity and everything. So that means that when we are going to get workloads which are kind of pathological in the sense that they have enormous amounts of small files, that will basically mean that we are wasting space. So GPFS 5, on the other hand, is a completely different animal, and that has a new variable subblock size, and it depends on the size of the physical disk block, and that basically decides into how many logical subblocks you can split it into. In our case, that means that it goes up to 512, which is a huge improvement. So this basically means that we have been planning for the upgrade for a long time, but it's been postponed due to other more urgent work. And the way that we were basically able to do this is that when we initially created those file systems, we basically just split the physical storage space in approximately half and half and created 2 physical file systems on the same cluster. And basically this means that we can just shuffle, as long as we are below 50% utilization of the full available storage capacity, we can shuffle the data around and format one file system at a time without having to go to tape or fetch replicas from another center in Sweden. And to be completely honest, we did a tape backup, so we pushed all the data objects to tape as well, just in case, but we are hoping not to having to resort to tape. And we are planning to do most of the work online, which means that we are using iRODS to shuffle the data, and that shouldn't basically cause any interruption to any logged in users or data transfers. And the only offline part of the work is the actual system upgrade and firmware upgrade of the storage cluster, which technically, according to IBM, could also be done completely online, upgrading one server at a time and maintaining quorum, but it was recommended to do it offline, and we want to minimize risks, so we're going to do that offline. And this was supposed to be done already, but as yours truly is on sick leave for the 3rd week, that work has been postponed. And just to give you a quick outline of what we're going to do is the following. First, obviously we turn off iRODS. We don't want any users while we are upgrading stuff. And then we go through all the possible thousands or tens at least different firmware images. Well, maybe almost thousands if you count the disks, at least hundreds. So we have to upgrade all host firmwares, partition firmwares, disk controllers, SAS controllers, storage arrays, disks, InfiniBand adapters, everything. And then upgrade the operating systems on the GPFS servers, and then finally upgrade the GPFS subsystem, and then finally we are good to go for the actual job. And basically here is where the more interesting part begins in step 8. we basically have already prepared ourselves by clearing out FS0, the first file system, into the second one called FS1. And basically we are good to go for destroying FS1 when we have the newer version of Gpfs available, and we can reformat those block devices. And then once that is done, we can use iRODS to migrate everything from FS1 to FS0, and then do the same for FS1. And after they have both been formatted with the latest version, we can just rebalance and split the resources evenly, and perhaps create a new set of new ones if we see the need for that. And the first step was done quite a while ago, because this work has been standing in line waiting to be done, and we were able to do this with the parallel rule execution engine. And with Jason and Terrell, we devised this process. We wrote these rules, the first of which basically just invokes an enormous amount of replication jobs per object from one set of resources to another. And the second one is a trimming job. So basically, after we have replicated everything, we need to trim away the old replicas from the old resources in the old file system, or that were originally in the old file system. And the rule file looks like this. So first, we use the built-in GEN query interface in the rule language, and we want to find all data objects that are residing within a certain path, virtual path, and within a certain resource. And then we start figuring out if this is an object that we want to replicate. So we basically want to check if this object is already present in the destination resource that we want to replicate it into, and we do another query. So this is quite heavy to run this, because it's basically has queries within queries and loops within loops. So it's not optimal, but it did the job very well. So after you discover if the object is the one that you want to replicate, you either skip it or don't. And if you decide to not skip it, we invoke Microservice Replication and enqueue the job. And basically, this is the way we replicated about 3.2 million objects. So there was in total of about 3.2 million jobs. Not at once though, but very many in the queue. And the second part, the trimming part, is simpler. It's basically just you do the same. You query all the data objects within a certain virtual path and resource, and then you just query the trim jobs. So enqueue the trim jobs. So obviously we needed lots of performance for this, because there are millions of jobs to be executed. So we turned the knobs into 11, and basically we set the maximum rule engine processes to 16. The database server has 20 cores in it. So we were first stressing it with 16 simultaneous jobs. And that didn't go over so well. We were able to drain all the database connections pretty quickly. So something went wrong. So we had to fall back to 8 simultaneous jobs. And even with that, there was still something that basically made the iRODS agent processes pretty hungry up for the database connections, and they apparently didn't manage to clean themselves up entirely quickly enough. So we were running about more than 1,000 agent processes simultaneously in the DB server. It didn't crash, but the load was very high. And this was just a quick screenshot that I sent to Jason about the CPU utilization on the storage node when it was running those replication jobs, and it was running parallel transferring and parallel checksumming jobs on the individual data objects. So we ended up getting quite a nice level of CPU utilization on the storage nodes as well, because iRODS itself doesn't do the checksumming in parallel. So we were running many checksumming jobs in parallel effectively. And this is another quick screenshot from the IBM monitoring system for the Gpfs cluster. And we were basically able to get, this is basically all iRODS traffic, which was peaking around 10 gigabytes a second. And almost everything went through, but there was 2 mysteriously failed files, or 2 mysteriously failed replication jobs, which were easily able to find from the logs. Then all I did was basically just run the thing again, and then it just nicely discovered that, oh, we have two objects that we need to replicate because they weren't previously replicated. And even after that, there was still one mystery data object when we were querying out the success rate of this previous mass replication jobs. There was one resource that was lacking one object. And we found out that that was a leftover of a test file by yours truly called big file. And that was in the orphan section of the trash. So that was quickly taken care of. And the very last part was the so-called trim jobs with the previously shown rule. And I just basically ran a lot of just queued up, well, a lot of those, and hope for the best. And there were some mysteriously failed trim jobs, not very many of those, but a few hundred that had to be manually checked after and requeued. And there might be a bug report coming from this once I figure out why it failed. We have been trying to figure it out, but not yet entirely. So I haven't submitted the bug report for that yet. There was a few other bugs that we discovered during the process, and those I believe have been fixed already. So it seems that I'm running out of slides and probably running out of time.
No, I think you're doing just fine. We've got about 10 minutes for the slot. So if we have some questions for you, I've got, thank you so much. That's great. And I remember doing that live and watching things drain, and it almost got to be even. It was great. We missed one and it was in the trash. It was the perfect answer.
Yeah. So just to point out, this was during Supercomputing 2019.
That's
we were
correct.
in Denver.
That's right. Last November.
Yeah. Fun week.
When we could be in airplanes and things.
Yeah.
So let's see. I've got a couple questions here. So Alan, first of all, apologizes for the connection draining issue with database. That's been fixed in 4.2.8.
No problem. That's fixed, right? So.
That's correct. Ton wants to point out that the delay server with a very small sleep time has given him trouble in the past. We now assure him that that's also been fixed in 4.2.8. It's now using, the internal is using iRODS query processor itself. So there's no way to hold it wrong, and it behaves well. It cleans up after itself. So had you done this year, it would have been much more well behaved and even cleaner.
Right. Can I point something out quickly?
Yeah, of course.
We are going to be able to exercise that because this process is still halfway. So if we upgrade to iRODS 4.2.8 before we do the rest of the shuffling, we can exercise that.
Yes, and that would be another great write-up to know about the before and the after. John Constable says, Do I understand that the resources don't have multiple replicas?
Correct. There is supposed to be only one replica per resource.
At the iRODS level.
Yeah.
Is Gpfs keeping multiple copies somewhere, or is that just the policy that you have in place is to only have one?
Gpfs itself, the Gpfs file systems have normally only one replica of the file, but now we of course had two at the time before we trimmed them. But
Okay.
the other set of replicas that we have, they are on top of the other ZFS-based resources. So we asynchronously replicate from Gpfs to the ZFS sets of resources.
Right. So your redundancy is not necessarily handled by the iRODS layer, but by the storage layer.
Well, both.
Depending on what it is.
Both. So there are many different layers of redundancy. The Gpfs cluster itself has RAID in it, or Gpfs declustered RAID, and then the ZFS pools are of course built with ZFS RAID, and then we use iRODS for replicating all data objects between those two sets of resources. The other set is in Stockholm, and the other set is in a completely different town. So even if Stockholm disappears from the map, we still should have everything. Which I'm not hoping to see, but you know.
John Constable has a follow-up. He says, now that you have done it this way, would you do it again? And I'm not sure exactly which part that he's talking about, but
yeah, I believe I would. It was interesting, but I think this is the most efficient way to do it. So that I have yet found out. So if I'm willing to experiment something else as well, but this, because we need to be able to do the shufflings in relatively short periods of time. So I don't think we want to wait for serial execution of the
right.
migrations.
Yeah, one other thing Jason has pointed out is that the query processor is now fully parallelized itself. So
Really?
like again, we said 428 is going to be much cleaner in terms of doing this if you did the same work again, or like you said, part 2. We have one question from Samuel at CNES. Is the maximum number of concurrent rule engine server processes similar to AC set RE server num proc in core.re? And I believe that those are similar, but one is set by the server config and one is set as a matter of policy. I believe that's the answer to that question, Samuel.
Yeah, I would have to refer to Carol on this one.
Alan has answered yes. Answer is yes from Alan. And then he links to it with an excellent example. So good job, Alan. Ton wants to know how many data objects were involved and did you use checksums everywhere? I think you answered
Yeah.
that. So
the total number was, I can actually show you the quick numbers if you want. It's
sure.
How does this screen sharing thing work?
We've still got about 5 minutes, so you're doing fine.
I can just basically open up a browser window somewhere, because this is in a blog post.
And then if you can do 2 things at once. These file systems were active and usable by users while you were doing this?
Yeah, nothing was halted.
That's right. So everything was available and the abstractions for iRODS held, and Ilari was able to do this,
I was
in the background, so to speak.
I was literally doing this while I was traveling to the US and while I was in supercomputing and while I was partying with you guys. And I mean, the system was running the jobs as we were partying. I wasn't typing at the time.
That's right.
And
so the question is, how many files, how many data objects are we talking about? And then the total size in terabytes, if you've got that.
Just a sec, I'll reset screen share. How does this work? New share from.
Well, you can just read it to us if that works.
Can you see this one?
Oh, yes, there it is. So this is a blog post on iRODS.org about the same work that Ilari just spoke about.
So you can find it in the news section, and you can see that here it was It's around 835,000 times 4. So that was the like 3.2 million data objects that were migrated, and this is about half of the total, because they are approximately split half and half between the two
That's right.
file systems. And the total data mass was, I think, around 100-ish terabytes.
You said about 100 terabytes? Okay.
Yeah, close to, not 100, but maybe 80.
Okay.
80-ish terabytes that we migrated, 3.2 million objects.
Very
Next
good.
time when we do it with the newer version, we can actually do some benchmarking while I'm not traveling and there's not a conference going on.
That's right. Very good. Thank you so much, sir. I hope you feel better soon.
Yeah, this made me feel
And
better.
we won't make you talk anymore unless you want to. Got many claps and bravos from Slack. Thank you, sir.
Thank you. Always a pleasure.